Welcome, everybody. It's my distinct pleasure to introduce today Chris McKay. He's a planetary scientist over at NASA Ames, and his talk today will be about the Phoenix Mars mission. I'll leave Chris to take over.
Thanks, Corey. What I want to talk about is the Phoenix Mars mission. Phoenix is on Mars right now, digging away in the dirt. It has another couple months before it gets buried with carbon dioxide, snow, and freezes up for the winter. What I want to do is just give you a short summary of the mission and update on its results. So the Phoenix Mars mission, the PI is Peter Smith at the University of Arizona. Phoenix is the first planetary mission that's being operated for NASA by a university PI. And it's really worked very well. And I hope NASA continues with that precedent. The University of Arizona built a separate building all by itself. It doesn't have a security fence around it, which is nice, and it's got ample parking. So thereby overcomes both problems of NASA centers and universities. My name is Chris McKay. I'm a science co-I on the mission. Phoenix launched last May on a trajectory to Mars, landed May 25th this year. Sorry, launched last August and landed May 25th of this year. Here it is being launched from the Cape. Here is a view of Phoenix being assembled. These are normal-sized people, so you get a sense of how big it is. These are the solar panels. Here's the lander deck itself. You see this bag? That's a biobarrier bag, and within that bag is the arm. The only part of the Phoenix lander which was sterilized was the arm. This is not well known, but we stopped sterilizing spacecraft to Mars after Viking. So the rovers, the Mir, Beagle 2, none of those were sterilized. Phoenix is not sterilized, but the arm was, because the arm is coming in contact with ice. And so for that reason, the arm was sterilized. And so it's in a sterile bag. When it got to Mars, it popped out of the bag. The reason it's called Phoenix is interesting, is that Phoenix is literally reborn from two previous missions. In the late 90s, NASA built two identical spacecraft with the intention of launching one in Mars 98 and launching the second one in 2001. The one in 98 crashed on Mars. It was lost. We don't know exactly how it was lost, although we now have a very good idea. It was lost, and as a result of that, headquarters canceled the 2001 mission for obvious reasons. You have two identical spacecraft, one crashes. You don't want that to happen again. A couple years later, several of us started pushing for rehabilitating that spacecraft, doing a test readiness review and getting it ready to fly again. And Mike Heck suggested we call it Phoenix for that reason, which we did. It was selected in a competition among many other spacecrafts, many other mission designs. Having a spacecraft already built really put us a leg ahead of the competition in terms of showing that we were ready to go and so on. Phoenix basically has 4 science instruments on it. It has a camera to look at on the surface. It has what's called the TIGA, thermal evolved gas analyzer, which is basically an oven which can heat up samples to 1,000 degrees, and then a mass spectrometer to look at the fumes that are released. So an oven and a nose. It has a wet chemical cell, a series of chambers where soil can be added, and then water and various electrolytes added to the soil. That's very important because this is the first wet chemistry done on Mars since Viking. And then it had a meteorological station, a LiDAR, a laser pointing up, looking at reflected light. That was the Canadian contribution to the mission. So those are the instruments. Phoenix landed, and when it landed, it was photographed on its descent from the Mars Reconnaissance Orbiter. So this is a photograph of Phoenix on the parachute coming down to its landing, taken from orbit, which I was amazed to see that photograph. Almost equally as amazing is the pictures of Phoenix on the ground. Here is the lander, here's its heat shield, here's its parachute. You can see, as I've blown up that image, the solar panels and the deck. There's no privacy on Mars anymore. Everything you do there is being watched. It's incredible. Phoenix was supposed to land at this little blue cross. It landed at this red cross, which was just at the edge of the 3 sigma air ellipse. So it landed off target. It landed successfully, but it landed off target. for us, on the Phoenix mission, that's not a problem. Phoenix didn't have to go anywhere after it landed. Its only success criteria was that it land on ice, and there's ice throughout this entire region. So as long as it landed safely, we were happy with it landing anywhere. But that is an issue for Mars missions in general, in that, particularly on the next mission, we want to land near something that we then rove to. And so having a many tens of kilometers error would be a serious problem. It turns out the reason it landed long was as it came in, it had a higher angle of attack than expected. And that resulted in it generating more lift than expected, and so flying longer than expected. So it flew a lifting trajectory. I was asking the engineers just last week, why did it have a higher angle of attack? And we still don't know the answer to that. Why did it have a higher than predicted angle of attack? So of course, the first thing Phoenix did when it landed was the first thing Viking did when it landed. The first thing I do when I get off the plane is look down and make sure your feet reach the ground. So this is the Phoenix looking down at its footpad. And then looking out and looking down was really quite spectacular. Looking out, we immediately saw that we were on the patterned ground, just like we see in polar regions on Earth. And looking down, we saw that the descent engines had blown away enough soil that the ice was visible right underneath the lander. So we were certainly on ice-cemented ground as expected. It wasn't a surprise, and it wasn't unexpected that there was ice at the landing site. It was not a discovery to find ice there, despite some of the press reports. We landed there because there was ice. This is the map that was the motivation for the Phoenix mission. This is the map of the hydrogen or ice distribution on Mars as derived by Odyssey. The dark blue indicates ice-rich regions, which are here in the northern hemisphere, here in the southern hemisphere. That's ground ice on Mars, ice below a thin layer of dry dirt, ice-cemented ground. Phoenix was targeted to land on that material, and we did at 68 degrees north. So we knew that there was ground ice on Mars. That site is particularly interesting to us because not now, but 5 million years ago, conditions may have been like they are in Earth's polar regions. So here is Mars today. It's tilted at 25 degrees with respect to the sun. So its seasons today are very similar to seasons on Earth, which has a tilt of 23.5 degrees. But 5 million years ago, Mars was tilted at 45 degrees, which means its seasons were exaggerated by almost twice compared to our seasons. As a result, the polar regions 5 million years ago would receive twice as much sunlight as they receive now. Twice as much sunlight is about the difference between Earth's orbit and Mars' orbit. So the Phoenix landing site 5 million years ago would receive about, roughly speaking, the same level of sunlight as the corresponding point in the polar regions on Earth. Question here?
How do we know what the tilt was 5 million years ago?
The question was, how do we know what the tilt was 5 million years ago? No one was there to record it, obviously, but we have computers that could simulate it, obviously. This is a calculation from last Gardel. It's a calculation of the orbital. It's taking the equations of motion for a planet and just integrating them backwards. Mars is a top. It's got an equatorial bulge. That bulge is torqued by the presence of other planets, principally Jupiter. So we can solve the equations of motion, in this case Euler's equations for a rotating object, and calculate backwards how the obliquity and eccentricity and inclination would have changed with time. Those calculations are accurate back about 10 million years, after which point the solutions become chaotic in a mathematical sense. And it may also be that the precise trajectory is not accurate, but in terms of the rough parameter space, it probably is. So that we know 5 million years ago, the obliquity was probably 45. It may not have occurred at exactly at that point, but for our purposes, that's really not essential. Okay, so why is this interesting? For me, I'm particularly interested in the question of the search for life on Mars. That's my area of interest. And the first step in searching for life is water. Well, to get water on Mars requires three things. First, it requires ice as a source for the water. It doesn't do any good to have warm, temperate conditions if there's no ice to provide the water, which the polar regions have. That map of ice shows where there could be water recently. Then it requires temperatures above 0 degrees, melting the ice. That's what we're familiar with on Earth. But a condition that's also important on Mars that is not important on Earth is that the pressure must be above 6 millibars. This is the so-called triple point of water. If the pressure is below 6 millibars, or even if it's close to 6 millibars, water behaves like dry ice does on Earth. It goes directly from solid to vapor, and a liquid phase is not possible. Right? Now, that is not part of our intuition of water on Earth, because on Earth, everywhere, the pressure is above 6 millibars. It's 100 times above. Pressure in this room is 1,000 millibars. So we tend not to think about that, but pressure is just as important as temperature in allowing water to exist as a liquid. Right? If you remember your basic thermodynamics, a state variable description requires two variables, pressure and temperature. And on Mars, in fact, the variable that controls the existence of liquid water, I would say now and through Mars's history, is not temperature as on Earth, but pressure. When we look back, this is sort of a footnote to the talk, but when we look back at Mars's history and we see evidence of water, I don't think we're seeing evidence of warmer conditions. We're seeing evidence of higher pressure conditions. Our intuition that we develop on Earth, which is focused on ice and temperature, misleads us a little bit when we look at Mars. Well, the North Polar regions on Mars are the key place for liquid water. Because Mars has a hemispherical topographic dichotomy, the North Polar regions are low elevation, the South Polar regions are high. The North Polar regions have pressures that are always higher, always above 6 millibar. There's ice at the surface, as we discovered by landing and as we knew before we went. Right now, those temperatures are always well below freezing, but 5 million years ago, as I said, temperatures might have been higher. So the polar regions on Mars and where Phoenix landed could have been or could be a habitable place 5 million years ago. And that's what I'm going to be talking about later as we compare it to similar places on Earth. Well, what did we find when we got there? Well, we found a lot of things that we expected, even though some of them were discussed in the press as if they were discoveries. Mars is red. We see that. It's cold. Minus 30 to minus 80. We saw on the surface rocks, dirt, and patterned ground, just as we expected. We saw a subsurface ice table, as expected. We would have been extremely surprised if there hadn't been ice below us, and disappointed too, I'd add. And we saw salts, sodium, magnesium, chloride, other salts, as expected. These were all as expected. There were really no surprises in here.
Was that real color or false color?
It's real color on my computer, and it's it's projected reasonably well here too.
I'm talking about is the camera itself a color camera? Or
Oh yes, the camera is a color camera. That's right. Sorry, I thought you meant the rendition.
Oh, I'm sorry,
Yeah, there's a color camera. That binocular camera is a color camera. And you see on this picture the scoop that picks up the dirt and does the sampling, and you're seeing a solar panel here. We also found things that were not expected. And this is the list of the things that we find that were not expected. The soil had a pH of 8. This was the first time we'd measured the pH on the soil on Mars. Hard to believe, 5 missions, and we still didn't know the pH of the soil. We've now measured it at one spot, and the soil appears to be buffered by carbonate, a few percent carbonate. Well, this was really curious because, as you may remember, one of the rovers, the Mir rover, landed in Meridiani, and it found what appeared to be an acid soil. It found jarosite in the soil, and jarosite is an iron sulfate mineral that forms a pH around 3. And so there was, and at the same time, the orbiters had failed to find carbonates, large carbonates, carbonate outcrops on Mars. So there was a consensus in the community that Mars was an acid world, and that it had an acid ocean, and that the acid explains the jarosite and the iron mineralogy and the lack of carbonates. And so to land here and find alkaline soils buffered by carbonate did a very nice job of puncturing that belief, and illustrating that Mars is a diverse place, and that finding one thing at one site doesn't allow us to extrapolate globally to the whole world. We also found at that site perchlorate. Perchlorate is the most, of the oxidized forms of chlorine, it's the most oxidized, and it was at about 0.5% concentration. These two conclusions are fairly solid, they're fairly unequivocal. The ones that are not yet quite so solid I put in yellow. from the TIGA results, we found no organics and no nitrates, which is interesting and a little bit disappointing from a biological point of view. It would have been great if we had found organics, and nitrates also would have been interesting, as one of the challenges for life is a source of nitrogen. Question here?
What about contamination from the descent rocket?
The only rocket that had perchlorate in it, perchlorate is used as fuel in solid rocket motors, but the only engines that had solid rockets were the liftoff engines, the strap-on boosters. The descent engines were hydrogen peroxide, so there's no perchlorate in them. The only possible contamination from on board might have been the explosive bolts, pyrotechnically activated bolts, and that it really is 0.5% is a lot of perchlorate, so it's not likely. No organics, no nitrates. This is a preliminary result, but I think it's going to hold. And that has, the implications of that are still sort of soaking into my head. There's no organics and no nitrates. And that rules out one particular energy source for life. We also found segregated ice, which I want to show you here, and then I'll go back to that slide. Segregated ice, that is, as I said, we expected ground ice, which is a table of ice cemented ground with dry permafrost above it. That's what we expected. We expected dry soil and then an abrupt boundary to ice cemented soil. And that's what we see in the bottom of these trenches. And if you're in the permafrost regions on Earth, you experience this directly. In the summer, you dig down, it's soft, and you hit what seems like a basement of concrete. That's the ice table. We found that. But we also found in the dry soil chunks of white material. It could have been salt, it could have been carbonate, could have been ice. After a few days, we saw that it was evaporating. If you look here and here, you see that it was evaporating. So it was clearly ice. That was unexpected. And I call it segregated ice in that it is not part of the ice table. It's little chunks of ice floating, icebergs in the dirt. Well, what are the explanations for this? There's three explanations that I've seen at least discussed in the team. One is that it's buried snow, simple but unlikely. The other is that it's also vapor deposited like that ice table is below it. That is, vapor from the atmosphere is condensing in the ground and just forming ice. That's a good explanation for the ice table, but I don't think it's a good explanation for this. We don't see that happening on Earth. I'll show you places where we have ground ice that's vapor deposited. We don't see that segregated ice. On Earth, if you see segregated ice, chunks of ice in dirt, it's always associated with action of liquid films and temperatures cycling between freezing, near the freezing point of those liquid films. So I think the Occam's razor explanation for that ice, segregated ice, is that it's a result of liquid films. In this case, as I'll argue, salty liquid films, not freshwater liquid films. Another interesting result that's consistent with salty action in the soil is the stickiness of the dirt. As you may remember, when we first opened the ovens, this is the door to the TIGA instrument, and you see the fine-grained screen there. That's to filter the particles coming through so that big chunks don't clog up the door. When we put the dirt on that screen, nothing fell through. And the instrument had a shaker on it, and they shook it, and still nothing fell through. And there was a couple days when we were wondering, are we going to get any data at all? It was sticking there like mud. And about 3 days later, it just started falling through. Now, one possible explanation for that is that it dried out, that it was a mix of ice and salt and dirt. And as it warmed up, it formed a mud mix of ice, salt, and dirt. And then as it sat there in the dry Martian air, the water left, and we had dry salt and dry dirt, and then it fell through. All of it pointing to the notion that there could have been salts on Mars. So it's useful to look at the weather report. Here is the weather for the first couple months. The average is maximum is minus 30, minimum is minus 80. Pressures above the triple point, but not a whole lot. The maximum minimum crossed the eutectic of several salts, which is, I think, an interesting observation. The eutectic salts, as you know, are antifreeze. They lower the freezing point of water, which is why in places that have winter, they throw salts on the road in the winter to cause a melting layer on the ice so that the roads aren't icy. If you live in the US, they probably use sodium chloride. But if you live up in Canada, it's too cold for sodium chloride because sodium chloride will only suppress the freezing point to minus 20. If you want to go to minus 30, you need magnesium chloride. And if you live in some really uninhabitable place in the far north, you want to put calcium chloride because that'll suppress the freezing point to -50. So these salts, magnesium chloride and calcium chloride, will cycle between liquid and solid in this temperature range. The minimum temperature at which a salt will suppress the freezing point is called the eutectic temperature. So these salts, if they were in the dirt and there was enough ice and enough salt, could go from solid to liquid and back through that temperature range. And I think that is a part of the explanation for the stickiness, and that's also could be what caused the segregated ice. Here's an example of the model for the stickiness, is that we have dry soil with salts and ice. As we dig, we mix some of the ice in with the salts that formed a eutectic brine, and it sat there as a muddy, salty mix on the spacecraft. And then when we it sat there, it dried out and went back to solid and then was able to fall through. And you can do this in the lab. If I take salts, like magnesium chloride, and mix it in with salt, with dirt, Mars simulant dirt and water, it becomes muddy and sticky. Not surprising. The salts also open up the possibility that there could be what I call a salt active zone. On Earth, the permafrost active zone extends from the surface down to the point where 0 degrees is reached. And that is the active zone, the zone that melts in the summer. If you had salts, for example, sodium chloride, that could be suppressed down to -21, the eutectic of sodium chloride. And so there might be a zone in which having a salt allows liquid to exist at temperatures below 0. And in fact, one of the things I'm doing right now is trying to find natural places on Earth where we have salt-saturated soils in polar regions and looking to see the physical manifestations of this phenomenon. So far, I haven't found one, but got to go to the poles and look. So what I want to do now is talk about putting the results from the Phoenix site on Mars in the context of our understanding of polar regions on Earth, and then and then follow that with some discussions of the biology of these regions on Earth. So this is sort of a diagram, schematic diagram of drier and colder conditions. And up here is Mars today, extremely dry, extremely cold. Here on the other end, I'm putting the Arctic. The Arctic is relatively cold and wet permafrost. You even can see a little bunny rabbit here. On this scale, it's the most habitable we'll consider. From the Arctic, going a little colder and a little drier is the coastal Antarctic. And then going a little colder and a lot drier, the high elevation Antarctic. And on Earth, we are able to cross the boundary between wet permafrost and dry permafrost. In the Arctic and the coastal Antarctic, we have what is called wet permafrost. This is permafrost that in the summer melts and has a layer of water above it. So the ice boundary, if you go digging in permafrost in the summer, the ice boundary will have a temperature of 0 degrees, and the depth of permafrost will be the depth of that 0 degrees isotherm. Wet permafrost. And that permafrost interacts with its environment, exchanging water through the liquid phase. But if it gets cold and dry enough, you reach a point where the permafrost does not melt ever, and the interaction with the environment is purely as vapor. And I call that dry permafrost or vapor exchange permafrost. There's only one place on Earth where we find dry permafrost, and that is in the high elevations of the Antarctic dry valleys. I should say there's only one place on Earth where we have found dry permafrost. I think there may be other locations where there is dry permafrost, where conditions are cold and dry. In addition to the dry valleys, I think the next likely place to find dry permafrost is actually at Earth's equator. At Earth's equator, but at high elevation. On Kilimanjaro and places like that that are persistently cold and dry, I think we also have dry permafrost, but they are less explored than the Antarctic. Now, if you think of that continuum on Earth, from wet permafrost in the Arctic, wet permafrost in the Antarctic coastal regions, to dry permafrost in the Antarctic high elevations, Mars is outside that continuum. Mars is colder and drier than even the coldest, driest permafrost on Earth today. But 5 million years ago, the model suggests that Mars was within that continuum. So right now, Mars today is an extrapolation of what we have on Earth, but 5 million years ago, Mars would have been an interpolation between what we have on Earth. So these communities on Earth bracket what Mars was like 5 million years ago, and they may allow us to extrapolate to what Mars is today. So for that reason, we dragged the Phoenix team down to Antarctica last January. Here's Peter Smith, the PI of the mission, and the rest of us here. I'm here as native guide to show them around. We were studying permafrost in the coastal regions and in the high elevation dry regions. Just to orient you, this is the dry valleys of Antarctica, the largest ice-free region in Antarctica. Straight south of New Zealand, here is McMurdo Station on Ross Island. The main US base is there. And here is the dry permafrost zone that we're interested. This is the dry valleys, and the dry permafrost that we're going to study is in these valleys up here, Beacon Valley and University Valley and Friedman Valley. The mean annual temperature in these valleys is -20 centigrade. It's very cold. The biggest difference between these valleys and Mars is not the temperature, it's that the pressure is well above the triple point in these valleys. Here's looking down one of the valleys, the Lake Vanda, the Onyx River. These valleys are the only place on Earth where it never rains. It's not that there's no hydrological cycle, but rain is not a part of it. It's only snow. Snow, the typical hydrological cycle in these valleys is snow falls to form glaciers, which flow downhill. Seasonal melting creates transient water, which flows in seasonal rivers to make ice-covered lakes, which then evaporate to close the cycle. It's the only place on Earth where it never rains. There's places on Earth where it rarely rains, like the Atacama Desert, for example. But even there, any precipitation that does come comes as rain. Here, it's only snow. So the coastal, what did we find there? Here is our camp at the coastal site where we found expected to and found wet permafrost. This is Lake Fritzl, our camp there. It's a well-established camp. It's been there for about 15 years, solar powered. It has wireless internet, if you can believe it. We spent Christmas Day here, and it was really quite comfortable. You see the pattern ground, just like we see on the Mars Phoenix site. When you dig a pit here in the middle of summer, Christmas Day, the height of summer, what we find is, as expected, soil that's dry, then soil that's wet, and then a temperature of 0 degrees and ice-cemented soil above it. This is classic wet permafrost in the summertime. Okay, now, moving up 1.5 kilometers in elevation, straight up, and 50 miles back in to this site, University Valley, no camp, no internet, no telephone, no nothing, just living in tents. Here we found dry permafrost, a very different physical system. We dig down through the ground and it's completely dry, bone dry. As I'll show you, I think it's the driest soils on Earth are right here. And then we hit ice-cemented ground, the temperature is -10. And this is the maximum temperature that this ice will reach in the summertime. In the winter, the temperature will drop to -40. So this is the dry, frozen soil. It's below freezing all year round. It's dry permafrost, and this is the ice-cemented soil beneath it. This is the Mars model. This is what we find on Mars is dry permafrost. We don't find liquid water in the transition between the ice-cemented ground and the dirt above it. So what I'm interested in is the biology of these sites. So this chart is a comparison of the microbiology of wet permafrost and dry permafrost. And as far as I can tell from the literature, this is the first time that anybody studied the microbiology of dry permafrost. What we find, this is an Arctic site at 78 degrees north, 78 degrees north, 78 degrees south, all wet permafrost, 2 Arctic and 1 Antarctic site. And then this is the dry permafrost. And the colored bands indicate different types of bacteria living in that permafrost. And in particular, I want to draw your attention to the yellow and orange bacteria. They're not really yellow and orange, but what the color code means is that the yellow are sulfur-reducing bacteria, and the red are anaerobic metal reducers. These are basically bacteria that we find in every single soil we've ever studied. We find them even in the dry, oxidizing core region of the Atacama Desert. We find these bacteria. They live in little anaerobic microsites within the soil. And those sites are generally created by little bits of water, creating little tiny stagnant ponds, microscale ponds. The only place we haven't seen these yellow and orange bands in soils is in this dry permafrost. It was quite a surprise to get back the results and find no anaerobic bacteria in these dry soils, which is what leads me to think that these are the driest, most oxidizing soils we've ever studied. It's also interesting that they're not devoid of life. There is a community here. It's a community that is basically heterotrophic oxygen consumers. They're eating organic material, they're breathing in oxygen. There's no anaerobic component to it, very, very little eukaryotic component to it. It's a community that's in an equilibrium with its environment, but very different than the communities in wet permafrost. This is not too big a surprise. It's consistent with what we would think. But it illustrates 2 points. One is that the dry permafrost in the high Antarctic is habitable. There's a community of organisms living there. They're living on organic material and breathing oxygen. They're doing the same metabolism that we humans do. Eat candy, breathe oxygen. Eat candy, breathe oxygen. Repeat. They're doing the same thing. And it's very different than in the wet permafrost. So if you remember my argument that Mars 5 billion years ago is between the dry permafrost and the wet permafrost, it would clearly say that 5 million years ago, Mars was no more harsh than the dry permafrost in the Antarctic is. And if life can be supported there, could life be supported in the dry permafrost on Mars? And so that's the analogy we want to make between the dry permafrost in Antarctica. We know that this boundary is inhabited, and the dry permafrost boundary on Mars. Today, we know that that temperature is too cold, but 5 million years ago, those temperatures could have been comparable. And I think that would allow us to conclude that 5 million years ago, the Phoenix site was habitable with respect to the availability of liquid water. There's enough liquid water available in ice-cemented ground at -10 to support life. The water is in thin films of unfrozen water that exist down to temperatures of about -20 on the boundary between ice and any sort of other material. But there's a big difference between what we see here and what we expect on Mars, in that, as I said, the energy source here is organisms consuming organic material with oxygen. Well, we don't have oxygen on Mars, and now we know that there's no organic material. We also know there's no nitrate, which is the next most likely oxidant that life uses in the absence of oxygen. But we do know there's perchlorate. We also know that organisms on Earth will use perchlorate as an oxidant if there's no nitrate available. So in a sense, we've got half the answer for Mars. Well, step one, we know that water conditions have been suitable. Step two is we know that from a point of view of an energy source, perchlorate would be a good thing if we can think of what would be the reductant that the organisms would be consuming with that perchlorate. It's not organic matter, which is the reductant that the organisms on Earth are consuming. It's got to be something else, presumably some mineral phase. So that's an interesting question that we're still working on. Then going down the logic, water, check. Energy, maybe. The next step, the next challenge that life would have on Mars, living at that ice boundary, is a source of nitrogen. We found what appear to be no nitrates in the soil. The nitrogen in the atmosphere is too low to support fixation. So that may be where we stumble in terms of speculating what could these organisms be using as a source for nitrogen. But I'm very excited about this because up to now, arguing habitability of Mars stumbled at the very first step. Is there an environment with water? Is there an environment with enough water to support life, with a water activity in the habitable limit? We're able to push that 1.5 steps further. We can say, yes, there's an environment with water, and there's an environment that we think almost has enough energy, and we're even up to the point of wondering about the nitrogen capability. So I think the Phoenix site is confirming what we thought when we targeted, that this is the most likely place on Mars to have been habitable in the recent past. I want to end by just pointing out a few, showing a neat picture. Recent observation, dust devils. We'd seen these from the Mir sites, and this is the first one we've seen from in the polar regions, a dust devil out on the surface of Mars. What do we do next? Well, obviously, the interesting thing about the Phoenix site is the ice. Unfortunately, Phoenix did not really have an instrument capable of sampling deep into the ice. It had an arm for scooping up the dirt, as I showed you, and it had a little rasp on the back of the arm of the scoop so that it could scrape the ice and get some ice samples. But what we really want to do is, in the next mission, a follow-up to Phoenix, is drill down into that ice. We didn't find organic material in the soil, but there may be organic material preserved in the ice itself. The ice may be acting like a casement, protecting the organic material from what we believe to be oxidants on the surface that would destroy it. So we'd like to get down into it. So the mission that we're trying to focus on now as a follow-on, we would like to have a 10-meter drill that drills down into the ice and samples at a depth to look for organics. And then beyond that, we'd like a mission that drills even deeper, 100 to 1,000 meters down deep to get into the ancient record of ice on Mars. Ice and permafrost in general is a very good way to preserve evidence of organic material and past life. We see that on Earth. You can go into the permafrost on Earth, drill down and find organisms that have been frozen for millions of years. If they're eukaryotes, they're dead, but if they're prokaryotes, if they're bacteria, they're still alive. You can recover them. We can recover bacteria on Earth from ice samples that we think are 8 million years old. On Mars, we might be able to drill down and find samples that are several billion years old. And that's the end, and maybe we now have time for questions. Question here? Oh, you're supposed to go to talk into the mic because this is being recorded. And
last I saw, the conductivity probe hadn't shown any conductivity in the soil. What's the explanation of that if there's water with salts?
Yeah, the question relates to the conductivity probe. There's a probe which has 3 prongs, and we can measure the electrical conductivity between them. It's a standard technique we use on Earth in polar regions. If there's ice at temperatures that are less than -20, there's a thin film of liquid that creates high conductivity if there's salts in the ice, and we can see it. There's 2 issues with operating that probe on Mars. One is if it's colder, if it's too cold, you can stick it into ice-containing material and it will read 0 conductivity. And the other, if it's got a lot of ice in it and it's hard, you literally can't get the needles in, which is a problem I had with it when I was testing it in Antarctica a couple years ago. In places where there was no ice, I could get the needle in, but it wouldn't read anything because it was dry. In places where there was ice, it was too hard to put the needle in. So there's some practical difficulties with the conductivity probe that make interpreting it hard. So I'm not yet aware of any results from that probe that have added to our understanding. Any other questions?
So I've heard several times about the sunlight failing and freezing the rover. Is there any expectation that it will come back out in the spring?
Yeah, the rovers, of course, are near the equator. And so winter is not very harsh for them. They're able to survive just by turning down operations and sort of hunkering down. We are in the polar regions, and winter is going to come real hard. It's going to be totally dark, and we're going to get buried in carbon dioxide. So the temperature will reach 150 Kelvin. So I mean, try this at home. Take your laptop, dump it in liquid nitrogen, and then see if it works. If it does, send me an email. Let me know what you did. That's really tough on batteries and electronic components. So I bet the engineers will ping it next Martian spring just for fun. But the expectation is that it will be as dead as a doornail.
So related to that, at temperatures like -30 and below, metals tend to get very fragile and mostly useless. How did you solve that engineering problem?
On the spacecraft, the only things that move is the arm and some of the actuators on the instruments, and those are kept warm. In particular, the biggest problem that, in general, we've had, my understanding from the engineers, is the lubricants on the joints and the motors. This is becoming a big problem for the next mission, MSL. It was originally designed with a lubricant, sort of a dry tungsten lubricant was how it was described to me, but it ended up failing at low temperatures, and so they had to go back to another lubricant, and as a result, the mission is constrained to land near the equator because it won't operate in the polar regions because it's too cold, because its design lifetime is a year, so it's got a Martian year, so it has to survive the winter. So the low temperatures is a serious engineering problem, and the focus of the problem seems to be on lubricants for joints and motors.
The mission cost overruns were pretty widely publicized. What did they end up being total, and how much do you think that affected other Mars missions?
Well, the celebrated mission cost overruns are for the mission that's being built right now, MSL. And that one is, the mission cost overruns on that have generated a lot of heat and a little bit of light. And they are seriously impacting the whole Mars program. And MSL may get delayed an opportunity 2 years. And if that happens, it's really very unfortunate for the program. And it could mean that that ends up pushing back the whole program 4 or 5 years. So MSL, which is a much bigger mission than Phoenix, the cost overruns are serious. And I understand the problem. One was this lubricant problem, and then the other was the sample acquisition tool. MSL is a huge rover. It's about the size of a Volkswagen Bug. And the front of it, it's got a huge tool for collecting and processing sample. And as I understand, they've ran into a lot of complications with the operation of that, which is also delaying delivery. And if it does slip and have to go another 2 years, that's a big problem. And you may remember about a year ago, there was a big hoopla from NASA headquarters about cutting back on missions, on instruments that were over budget for that mission, MSL. Now, Phoenix had some problems with cost overrun, but most of them were driven by a extensive, maybe overextensive test schedule based on concerns about the landing and the failure of the previous mission. But the real problem with cost overruns is MSL, the new mission, the rover mission coming up.
Chris, putting planetary protection protocols aside for the moment, is there any organism on Earth that could live on conditions that we found on Mars today?
No, we don't know of any place on Mars right now where any organism from Earth could live. So that's a scientific assessment. So in fact, we try to find places on Mars where an organism could live. That's a goal from a science point of view. From a regulatory point of view, though, they take a different perspective. They say, can you rule out the possibility that there would be a place where organisms could live? Well, we can't rule that out. So they take a much more conservative approach. So the ice at the Phoenix site, from a science perspective, that's not a habitable spot. But from a planetary protection perspective, that's close enough to habitability that we're required to sterilize. So it's a question of whether you believe it versus whether you can prove it's not possible. For planetary protection, we have to prove it's not possible. To publish a scientific paper, you have to believe it. And that's the difference. So you end up with this sort of dual perspective. I say it's not habitable, but planetary protection says you've got to sterilize the rover in case something can grow. And those two are only consistent when you have those double standards.
You sort of just answered my question, but I was surprised to learn that we don't sanitize most of the components that we send. Can you talk about that?
Yeah, that's a good point. I always bring it up because everybody is surprised to learn, because there's a general perception that we sterilize spacecraft. And NASA actually continues to propagate that impression, that we sterilize spacecraft, but we don't. After Viking landed, the National Academy of Sciences and the Committee on Space Research, following the recommendation of the National Academy of Science, said, stop sterilizing spacecraft to Mars. It's not necessary. And so there's a cleanliness standard. So we know that the spacecrafts are pretty clean, cleaner than the kitchen in my house, but they still have bacteria on them. We know that the two rovers each went to Mars with about 100,000 bacteria on each of them. And most of those bacteria have been killed by being exposed to Martian UV, but any bacteria inside the spacecraft, they're still alive. They're not growing, but they're viable. They're dormant on Mars. So we know for a fact, it's not even conjecture, we know for a fact that there are Earth bacteria viable on Mars inside Sojourner rover, Pathfinder lander, and the two MERs. Inside, protected from UV, they're still viable, but they're not growing, and they won't ever grow unless they come across an environment with liquid water, which may not happen naturally on Mars, but who knows? So it's an issue. As we start doing more ambitious missions like drilling, we have to worry more about that, because in a drilling mission, drilling down, we might hit liquid water, and then if we contaminate it, it would be a serious problem, which is why things like the arm or a drill would be sterilized, because they're going separately. So this whole question of cleanliness and planetary protection and forward contamination are issues that we're still working. And when you imagine sending humans to Mars, we certainly can't sterilize them. How do you take that approach? Lake Vostok is a place on Earth where we worry about that as well, yeah.
So you mentioned that Phoenix is going to get buried in snow. Can we expect photos of like the lander feet covering in snow, or do we expect the instruments to break down before that happens?
Yeah, it's a good question. Will we be able to see the snow coming, or will we die in the cold?
We've already seen snowflakes, right?
No, well, high in the atmosphere. Yeah. The LiDAR detected snow falling, but we haven't seen any white stuff on the ground. Sort of like living in San Francisco. You know, you can hear about snow, and you know theoretically it's snowing, but the ground never actually turns white. And that's what we're experiencing so far. So I think if it, my guess is that we will see snow pictures before we lose the spacecraft. In time for Christmas, certainly in time for Christmas, yeah. Yeah, by Christmas time she'll be dead, yeah. Because we're already getting sunsets and darkness, and they're already talking about shutting down various parts of the spacecraft. So by Christmas, we'll probably be no longer talking. Any other questions? No?
Hello. The recent observations of ice lenses in the soil, as well as the liquid water around them, begin to constrain the mechanical properties of it. What is the team's thought on that observation with the local landscape geology that they see?
So here are these ice lenses in the soil. This I think is a major mystery, and it was unexpected. What is this ice in the middle of the dirt layer, and how did it get there, and how long has it been there? It's much softer, at least in parts, than this ice-cemented ground below it. And I was mentioning that on Earth we can go to a place where there's vapor-deposited ice-cemented ground in the dry valleys. We don't see this included ice. We don't see ice in the dirt above it. In the dirt above vapor-deposited ice on Earth, it is clear and dry. So we're not sure what's causing this. There's several possible explanations. That it's buried snow, vapor deposit, or liquid films. I think it's liquid films, but in any case, I would like to find a place on Earth where we see a similar phenomenon. So one of the things that we will do next time we go to the dry valleys, now armed with this knowledge of what Phoenix saw, is look in the dry permafrost on Earth to find a similar phenomenon, a place where there's a basement of ice-cemented ground and then dry permafrost, and in the dry permafrost, there's chunks of ice. If we find that, then we have a model here on Earth of what's happening on Mars, and that puts us way ahead of the game. I don't remember seeing it, but I never looked for it because I didn't know we were going to find it on Mars, so we never looked for it. But next time we go to the dry valleys, we'll look for it. And hopefully we'll find something like it, or conclude that it's a phenomenon unique to Mars and it doesn't have a counterpart in those limited regions on Earth where there is dry permafrost. Okay, good. Thanks, everybody.